Assalamualaikum and hi, we are from Group 4. We'll present about the effect of various acid solution on the extraction and absorption efficiency of chitin from shrimp shell waste. Before we start our presentation, I will introduce my group member, which is Nurul Aina Najwa binti Ruslan, Nur Azana binti Azhar, Nur Aisyah binti Ayub, Nur Fahana binti Helmi. Before we start our
Assalamualaikum and hi, my name is Nur Azana binti Azhar. The abstract of this topic is the Fourier transform infrared FTLR and X-ray diffraction XRD indicate the present the functional group. The isomorph of the obtained chitin diffractogram support the A-chitin structure and demonstrate the type of acid solution used. The study can conclude that the extraction and development of chitin not only saved the environmental, but it also had to decrease the cost of industrial wastewater treatment. Demineralization on this more effective to the strong acid, which is H2SO4 following by HNO3, HCl and HC3COOH. The best acid for removing RBBR derived from an aqueous solution is H2SO4.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurul Aina Najwa binti Ruslan. Today I'm going to present the introduction for this topic. What is shrimp shell waste? Shrimp shell waste is a major source of chitin, which accounts for around 15 to 40% of the dry weight of shrimp shell. Shrimp shell waste has been taken into account as one of these high calcium waste products. A relative vast amount of this material sit unused in landfill throughout the world, posing a serious environmental problem in a number of nations. Waste shells are a low-cost, reliable option that will reduce production costs while also decreasing environmental impact. To reduce construction reliance on virgin resources, attempts have been undertaken to include byproduct waste from other sectors as concrete alternative. Chitin may be found in fungal cell wall, insect exoskeleton, and crucial shells. Chitin is an insoluble linear homopolymer of polyethylene and acetylglucosamine and the second largest carbohydrate polymer in nature. Because of its strong biocompatibility, antibacterial activity, and biodegradability, it is frequently employed in medicine, biotechnology, nutrition, and food processing. As an environmentally friendly and efficient method, the extraction method of chitin from shrimp shell waste has been applied in the industry. In industry, the chitin has been produced mainly as a potential adsorbent for wastewater treatment. There are two types of chitin, which is biomass to produce chitin and extraction method. In these studies, the most effective method chosen is to extract chitin from shrimp shell waste by demineralization and deproteinization, which is removal of mineral and protein during extraction process. The different types of extraction have been used in the extraction and extraction to remove mineral and protein, plus to compare which type of acid produce high yields of chitin from shrimp shell waste. Okay, the objective of this project that we identify are as follows. First, the research objective of this project is to look into the effect of 4 different acid solutions on the extraction and characteristics of chitin from shrimp shell waste. Second, the objective of this topic is the aim of this is to assess the chitin absorption effectiveness in removing dye from an aqueous solution. And last, the objective is to analyze the cytochemical characterization of chitin extracted utilizing Fourier transform infrared spectroscopy, X-ray powder diffraction, and scanning electron microscope. That's all from me. Thank you.
Assalamualaikum, my name is Nur Aisyah binti Ayub. I will explain the method extraction of chitin. Chitin was extracted from shrimp shell using two methods, which is deproteinization and demineralization. First, 50 grams of dry powder shrimp shell were deproteinized in unalkaline treatment with 1 mole of sodium hydroxide solution at 90 degrees Celsius for 3 hours. After deproteinization, the shell powder was thoroughly washed with distilled water until the pH reached neutral. After that, the sample was dried in an oven at 60 degrees Celsius for 24 hours. Demineralization was achieved by treating the dry sample after deproteinization with 1 mole solutions of various acid, which are hydrochloric acid, nitric acid, sulfuric acid, and acetic acid at 60 degrees Celsius for 3 hours. The physical-chemical properties of the separated chitin were studied using FTIR, XRD, and SEM to highlight the influence of different kinds of acid solutions. Additionally, the absorption performance of chitin in demineralizations using different acids solutions was tested for the removal of Ramosal Brilliant Blue R (RBBR) dye from aqueous solutions.
Assalamualaikum and hi everyone. My name is Nur Farhana binti Helmi and I will continue this presentation with result and discussion. So let's start it. For chitin extraction and chemical composition, as shown in the graph above, the result shows that the composition of the raw shrimp shell powder after the demineralization and deproteination, which the extraction of chitin requires to remove the protein and mineral in order to get a minimal level as possible. Graph above evaluate that the composition of the protein decreased from 50.55% to 1.24% after the process deproteination by using an aqueous solution of 1 mol NaOH. For information, process deproteination might be slightly slower degree of mineral content due to NaOH only can remove some minerals from the shrimp shell but not significantly. Next, for the demineralization, the strong acid, which is H2SO4, produce low yield of chitin with low mineral content. However, the weak acid, which is CH3COOH, extract high percentage of yield with higher mineral content. Thus, it shows that the stronger the acid, the lower the mineral content with low yield of chitin. It can be treated as a result of degradation under extreme circumstances, as well as the loss of a tiny quantity of chitin during the washing process. The washing procedure with distilled water to remove the residual acid appears to have resulted in the loss of chitin. As a result, while washing the demineralization product with distilled water, care must be given to avoid losing the acquired of chitin. Next, for FTIR analysis, the functional group of the recovered chitin were identified using FTIR. Chitin may be classified into 3 allomorphs based on the orientation of its microfibrils. First, chitin anti-parallel change, chitin parallel change, and chitin parallel change, the recombination of parallel and anti-parallel change. Table 2 shows the pattern that related to chitin. Regardless of the kind acid solution utilized in the demineralization procedure, same absorption patterns were found for the produced chitin. Thus, FTIR result shows that demineralization with various acids had no effect on the structure of the resulting chitin. Last but not least, for the crystalline structure of chitin, the X-ray diffraction was used to determine the crystalline structure of chitin from different types of acid solution. As previously mentioned, the process of remove mineral by using CH3COOH generate the high content of mineral. This can be seen from the diffractogram, which is a small peak near to 20 equal to 30 degree that might be sulfide and calcium phosphate family. This can be proof that the weak acid cannot extract chitin from shrimp shell waste due to it was removed high content of mineral from the shrimp shell. Chitin treated with strong acid hide the crystalline index. It can be happens as a result of the rapid loss of chitin's amorphous domains during the acid demineralization process. The chitin produced using CH3COOH, on the other hand, had the lowest crystallinity index, which might be attributed to the poor elimination of amorphous domains. Thus, to get CRL levels comparable to those produced with strong acid treatment, the chitin recovered from shrimp shell waste using acetic acid must be further demineralized. That's all from me. Thank you.
So, the conclusion on this topic is we can be seen that the weak acid produce high yield of chitin but remove low mineral content. Opposite to the strong acid, which is H2SO4, it can be said that the strong acid generate low yield of chitin with high low mineral content. As the aqueous solution high acidity, the yield of chitin produced is low.
The absorption of RBBR onto the chitin surface demonstrated that increasing the initial dye concentration resulted in a decrease in dye removal percent and increasing in absorption capacity, which is connected to the porous ability driving force between absorbent and adsorbents. The Furley's absorption isotope was discovered to accurate analysis the absorption of RBBR onto the surface of the extracted chitin. Chitin created by demineralization with H2SO4 has a larger absorption capacity than that made by the other acid solution. This may be attributed to high mineral removal and big pores.